Welcome to this coding problem walkthrough. In this session, we'll explore LeetCode problem number 1489, find critical and pseudo-critical edges in minimum spanning tree. This is a fascinating problem that delves into graph theory and the concept of minimum spanning trees. We'll break it down step by step and analyze the solution approaches. Let's dive in. In this problem, we are working with a weighted, undirected graph that has n vertices, numbered from 0 to n1. The graph is described by an array called edges, where each edge is represented as a triplet, u_i, v_i, weight_a. This indicates a bidirectional edge between nodes u_i and v_i with a weight of weight_i. Our goal is to analyze the graph in the context of its minimum spanning tree, or MST. An MST is a subset of the graph's edges that connects all vertices without forming any cycles, while minimizing the total weight of the edges included. Now, the problem introduces two specific types of edges: critical edges and pseudo-critical edges. A critical edge is one that, if removed, either increases the total weight of the MST or makes it impossible to form an MST. On the other hand, a pseudo-critical edge is one that can be part of at least one MST, but it is not necessarily included in all MSTs. The task is to return two lists, one containing the indices of all critical edges, and the other containing the indices of all pseudo-critical edges, based on their positions in the input edges array. The output of the problem is straightforward. We'll return a list containing two arrays. The first array includes the indices of all critical edges, and the second array includes the indices of all pseudo-critical edges. To clarify how this works, let's look at an example. Suppose we have a graph with 5 vertices in the following edges: 0, 1, 1, 1, 2, 1, 2, 3, 2, 0, 3, 2, 0, 4, 3, 3, 4, 3, 1, 4, 6. The output for this graph would be 0, 1, 2, 3, 4, 5, 6. This means edges at indices 0 and 1 are critical, while edges at indices 2, 3, 4, 5, and 6 are pseudo-critical. To give you a better understanding, we'll also visualize the graph. Here is how the graph looks, with nodes 0 through 4 connected by edges of varying weights. In this graph, the minimum spanning tree includes the edges 0, 1, 1, 2, 2, 3, and 0, 3. The total weight of this MST is 6. Now, let's identify the critical edges. Removing edges 0, 1, or 1, 2 would either increase the total weight of the MST or make it impossible to form one. This makes them critical edges. On the other hand, edges 2, 3, 0, 3, 0, 4, 3, 4, and 1, 4 can all be part of some MSTs, even though they are not required in all of them. This makes them pseudo-critical edges. By analyzing the graph and systematically removing edges, we can determine which edges belong to which category. Now let's look at another example. Here, we have 4 vertices in the edges 0, 1, 1, 0, 2, 1, 1, 2, 1, 1, 3, 4, 2, 3, 4. For this graph, the output is 0, 1, 2. The visualization of this graph shows that the MST includes the edges 0, 1, 0, 2, and 1, 2, with a total weight of 3. This makes all 3 edges 0, 1, 0, 2, and 1, 2 critical. Removing any of these edges would increase the weight of the MST. However, there are no pseudo-critical edges in this graph, as no other edge can be included in an MST without violating the conditions of minimal weight or acyclic structure. To summarize the constraints and edge cases, the graph must have between 2 and 100 vertices. The number of edges can range from 1 to the minimum of 200 or the maximum number of edges allowed in a complete graph with n vertices. Each edge must connect 2 distinct vertices, with weights ranging from 1 to 10 to the power of 5. Important edge cases include disconnected graphs, where no MST can be formed, graphs with a single edge, where that edge is both critical and pseudo-critical, and graphs with multiple MSTs, where pseudo-critical edges may exist. By carefully analyzing the graph and applying these principles, we can determine the critical and pseudo-critical edges efficiently. To solve the problem of identifying critical and pseudo-critical edges in a minimum spanning tree, we need to classify edges based on their roles. Critical edges are those that, if removed, prevent the MST from forming or increase its total weight. On the other hand, pseudo-critical edges are not strictly necessary for the MST but could still be part of some valid MSTs. One way to approach this is through brute force, where we try all possible spanning trees. For each edge, we remove it to see if the MST becomes disconnected or its weight increases, and we also force its inclusion to check if it can still form an MST. While this method is straightforward, its time complexity of O, E asterisk, E plus V, where E is the number of edges and V is the number of vertices, makes it computationally expensive and impractical for large graphs. To address this inefficiency, we turn to an optimized approach using Kruskal's algorithm, which leverages sorting and the union-find data structure for a more scalable solution. The optimized approach begins with sorting all edges by their weights. Once sorted, Kruskal's algorithm is applied to compute the MST weight, which we refer to as MST_weight. This serves as our baseline for comparison. To classify the edges, we perform two checks on each one. First, we exclude the edge from the graph and recompute the MST. If the MST weight increases or the graph becomes disconnected, that edge is critical. Next, we force the inclusion of the edge into the MST and recalculate the weight. If the new MST weight matches the baseline MST_weight, the edge is classified as pseudo-critical. By processing each edge independently, this approach avoids the inefficiency of generating all spanning trees, offering a significant improvement in performance while maintaining clarity. The optimized approach using Kruskal's algorithm is our chosen strategy because it strikes a balance between efficiency and clarity. The process begins with pre-processing the edges, where we assign an index to each edge for easy identification and then sort them by their weights. Next, we set up a union-find data structure to manage connected components during Kruskal's algorithm. We compute the baseline MST weight, MST_weight, which serves as the reference for classifying edges. For each edge, we apply the two key checks to determine if it's critical or pseudo-critical. This approach has a time complexity of O, E squared asterisk alpha, V, where E is the number of edges, V is the number of vertices, and alpha is the inverse Ackermann function, which is nearly constant in most practical cases. By leveraging the efficiency of union find and the sorted order of edges in Kruskal's algorithm, we achieve a scalable solution that avoids unnecessary computations. One key observation that simplifies this problem is realizing that forcing an edge's inclusion or exclusion allows us to classify edges without needing to construct all possible MSTs. This insight leads to an elegant and efficient solution using Kruskal's algorithm, which takes advantage of sorting and the union-find structure to manage connected components efficiently. When comparing approaches, brute force is conceptually simple but computationally prohibitive for large graphs due to its high time complexity. While Prim's algorithm can also compute MSTs, it is less suited for this problem because it doesn't rely on globally sorted edges, which are essential for edge classification. The optimized approach, therefore, stands out as the best choice. It is efficient, scalable, and leverages the structure of Kruskal's algorithm to minimize redundant calculations, making it well suited for solving this problem effectively. In this problem, we are tasked with finding two special types of edges in a graph: critical and pseudo-critical edges. Critical edges are those that are essential for forming the minimum spanning tree, or MST. If we remove one of these edges, the MST either can't be formed at all or its total weight increases. On the other hand, pseudo-critical edges are those that can be part of a valid MST, but their presence isn't strictly necessary. The graph is given to us as an edge list, where each edge connects two nodes and has an associated weight and index. This structure will be the foundation for our algorithm as we determine which edges fall into each of these categories. To solve this problem, we begin with two key steps. First, we sort all the edges by their weights. This step is crucial because MST algorithms like Kruskal's process edges in ascending order of weight, ensuring we always construct the tree with the minimum total cost. Sorting can be done efficiently using built-in methods like Python sorted or Java's arrays.sort. Once the edges are sorted, we implement Kruskal's algorithm to compute the MST for the entire graph. Using a union-find data structure, we can efficiently manage the connected components of the graph. Starting with an empty MST, we iterate through the edges, adding each one if it connects two different components. This process continues until we have included exactly n1 edges, where n is the number of nodes in the graph. The result is a minimum spanning tree, and we store its total weight for further analysis. With the MST computed, we now focus on identifying critical edges. For each edge in the graph, we temporarily remove it and recompute the MST using Kruskal's algorithm. If excluding the edge prevents the formation of an MST, meaning the resulting tree has fewer than n1 edges, or if it increases the total weight of the MST, then the edge is critical, and we add it to the critical list. Next, we identify pseudo-critical edges. For this, we force the inclusion of each edge by adding it to the MST at the start of the Critical process. If the resulting MST has the same weight as the original, the edge is pseudo-critical, and we add it to the pseudo-critical list. Finally, we return the critical and pseudo-critical lists as the solution to the problem. Understanding the characteristics of critical and pseudo-critical edges provides deeper insights into the problem. Critical edges are indispensable, their absence disrupts the MST or raises its cost. In contrast, pseudo-critical edges can be part of the MST without affecting its weight, but they aren't strictly necessary. Efficient management of connected components is key to solving this problem, and the union-find data structure plays a central role here. Union-find allows us to quickly determine whether two nodes belong to the same component and efficiently merge components when needed. The find operation identifies the representative of a node, while the union operation merges two components. By using optimizations like path compression and union by rank, these operations run in nearly constant time, making the algorithm highly efficient. The edge list representation of the graph is another important element of the solution. It stores all edges along with their weights and indices, enabling efficient sorting and processing. Sorting the edges by weight takes O, E * log, E, where E is the number of edges. Kruskal's algorithm further processes these edges in O, E * alpha, the time, where alpha is the inverse Ackermann function, a very slow-growing value. However, since we must consider each edge for removal and forced inclusion, the additional processing adds a complexity of O, E * E plus V. As a result, the overall complexity of the algorithm becomes O, E squared plus E * log, E. Finally, we must account for edge cases, such as graphs with no edges, multiple MSTs with the same weight, or disconnected graphs. These scenarios highlight the importance of both critical and pseudo-critical edges in our solution and ensure that the algorithm handles all possible inputs effectively. To solve the problem of finding critical and pseudo-critical edges in a minimum spanning tree, we begin by defining a class and function structure. First, we modify the input edges by appending their original indices to keep track of their positions after sorting. Then, we sort all edges based on their weights, which is fundamental to the Kruskal's algorithm approach. After this, we define a helper function called find_MST_weight to compute the weight of the MST for given edges. Inside this function, we initialize the union find data structure with a parent array representing connected components and a rank array to optimize union operations. The find function uses path compression to efficiently determine the root of a node, which helps in keeping the union find structure flat. The union function combines two components based on their rank, ensuring that the tree height remains minimal. This setup will allow us to compute MST weights dynamically as we include or exclude specific edges. The union function is implemented with logic to handle the rank comparison. If one root has a smaller rank, it becomes the child of the other root. If the ranks are equal, we arbitrarily choose one root to become the parent and increment its rank. This ensures efficient merging of components. Next, we initialize the MST_weight to 0 and edge_count to track the number of edges in the MST. If an edge is mandatory, specified by the include_edge parameter, we process it first by extracting its details and attempting to union its nodes. If the union is successful, we add its weight to the MST and increment the edge count. After this, we iterate through all edges, skipping the one specified by exclude_edge if necessary. For each edge, we attempt to union its nodes. If successful, we update the MST weight and edge count. This logic ensures that we process edges in the correct order and efficiently build the MST. Finally, the helper function returns the MST weight if we successfully use exactly n1 edges, where n is the number of nodes. Otherwise, it returns infinity to indicate that forming a valid MST is not possible. Using this helper function, we first compute the weight of the MST without any restrictions. Then, we initialize two lists, critical to store the indices of critical edges and pseudo_critical to store the indices of pseudo-critical edges. For each edge, we check if excluding it increases the MST weight, which would indicate that the edge is critical since its removal prevents forming the original MST. Conversely, if including the edge results in the same MST weight, the edge is pseudo-critical because it can be part of at least one valid MST. Finally, we return these two lists as the output, representing critical and pseudo-critical edges respectively. Here, we start by importing the necessary packages and defining our solution class. The main method we're implementing is find critical and pseudo-critical edges, which accepts the number of nodes n and the list of edges, and returns two lists, one for critical edges and another for pseudo-critical edges. To begin, we add an index to each edge to track their original order since we'll be sorting them later. We then create a new array, extended edges, to store this additional information. Next, we sort the edges based on their weights using Java's built-in arrays.sort method with a custom comparator. Sorting by weight is crucial because it ensures we can process edges in the order required for building a minimum spanning tree, or MST. Following this, we define a helper function findMSTWeight to calculate the weight of the MST, allowing us to optionally exclude or include specific edges during the computation. This helper function uses the union find data structure to efficiently manage connected components of the graph. When calculating the MST weight in the helper function, we first check if there's a mandatory edge to include, represented by the includeEdge parameter. If an edge is to be included, we add its weight to the MST and increment the count of edges used in the tree. After this, we process all the remaining edges in sorted order, skipping the one specified by the excludeEdge parameter. For each edge, we attempt to union its two nodes using the union find structure. If the union is successful, it means the edge connects two previously separate components, so we add its weight to the MST and increase the edge count. Once all edges are processed, the function checks if the MST contains exactly n1 edges, which is the criterion for a valid spanning tree. If this condition is met, it returns the MST weight, otherwise, it returns integer.max_value to indicate the spanning tree is invalid. After calculating the MST weight for the entire graph without exclusions or inclusions, we initialize two lists, critical for critical edges and pseudo-critical for pseudo-critical edges. The next step is to examine each edge in the graph to determine if it belongs to either category. To determine if an edge is critical, we use the helper function findMSTWeight with the edge excluded. If the resulting MST weight is greater than the original MST weight, it means the edge is critical since the graph cannot achieve the same MST without it. We then add the index of such an edge to the critical list. Conversely, to check if an edge is pseudo-critical, we use the helper function again, this time including the edge explicitly. If the MST weight remains the same as the original MST, it means the edge can be part of the MST but is not strictly necessary, so we add its index to the pseudo-critical list. After processing all edges, the method returns a list containing the two categories, critical edges and pseudo-critical edges. This logic ensures that we systematically evaluate each edge's importance to the overall MST, leveraging the use of the union find structure for efficient connectivity checks. Finally, we define the union find class, which is a key component of the algorithm. It includes two arrays, parent, which keeps track of each node's parent in the disjoint set forest, and rank, which helps optimize the union operation by keeping the tree height minimal. The find method employs path compression to flatten the structure of the tree, ensuring that all nodes point directly to the root for faster future lookups. The union method merges two sets by connecting their roots, using the rank to determine the direction of the union. If the ranks are equal, the rank of the new root is increased. This optimization ensures that the union find operations remain efficient, with nearly constant time complexity. Together, the find and union methods enable the MST algorithm to efficiently manage connectivity while determining critical and pseudo-critical edges in the graph. In this example, we start with 4 nodes and the given edges. First, we assign an index to each edge for tracking purposes, resulting in a modified edge list. Then, we sort these edges by their weights in ascending order to ensure we process the lightest edges first. Now, using Kruskal's algorithm, we begin building the minimum spanning tree, or MST. We include edges one by one from the sorted list, checking for cycles using the union find data structure. The first edge connects nodes 0 and 1 with a weight of 1, so we union these nodes, and the MST weight becomes 1. Next, we include the edge connecting nodes 2 and 3, also with a weight of 1, bringing the MST weight to 2. Finally, we add the edge connecting nodes 1 and 2 with a weight of 2, forming a complete MST with a total weight of 4. At this point, we identify critical edges by excluding each edge one at a time and recalculating the MST weight. If excluding an edge increases the MST weight, that edge is critical. Here, we find that excluding edges 0, 1, 2, 3, or 1, 2 results in an MST weight greater than 4, so all three are critical edges. However, when we exclude the edge 0, 3, the MST weight remains 4, meaning this edge is not critical. Next, we identify pseudo-critical edges by forcing each edge to be included in the MST and checking the resulting MST weight. If the weight remains the same as the original MST, the edge is pseudo-critical. Here, including each of the edges 0, 1, 2, 3, 1, 2, or 0, 3 results in an MST weight of 4, so all four edges are pseudo-critical. The final output for this example is two lists, the first containing the indices of critical edges, and the second containing the indices of pseudo-critical edges. The result is 0, 2, 1, 0, 2, 1, 3. Now, let's consider the second example with 3 nodes and the given edges. We begin by appending indices to each edge for tracking, which results in a modified edge list. Since all edges have the same weight, the edges are already sorted. Using Kruskal's algorithm, we build the MST by including edges in order. The first edge connects nodes 0 and 1 with a weight of 1, so we union these nodes, and the MST weight becomes 1. The next edge connects nodes 1 and 2 with a weight of 1, completing the MST with a total weight of 2. When identifying critical edges, we exclude each edge one at a time and recalculate the MST weight. For all 3 edges, excluding them still allows us to form an MST with the same weight of 2, so none of the edges are critical. For pseudo-critical edges, we include each edge forcefully and verify the MST weight. For all 3 edges, including them results in an MST weight of 2, so all 3 edges are pseudo-critical. The final output for this example is 2 lists, an empty list for critical edges and a list containing all edge indices for pseudo-critical edges. The result is 0, 1, 2. To analyze the time complexity of this solution, we start by breaking down the key operations involved. The first step is sorting the edges by their weights. Since sorting has a time complexity of O, E * log, E, and E is the number of edges, this dominates the initial phase. Then, we focus on constructing the minimum spanning tree, which is achieved using the helper function find_MST_weight. This function relies on the union find data structure. Within union find, the find operation, which uses path compression, has an almost constant time complexity of O, alpha, V, where alpha is the inverse Ackermann function, and V is the number of vertices. Similarly, the union operation also takes O, alpha, V, per operation. Constructing the MST involves processing up to E edges, so this task takes O, E * alpha, V, for one call to find_MST_weight. Since this function is called twice for each edge, once to check if the edge is critical and once to check if it is pseudo-critical, the contribution from this step becomes O, E² * alpha, V. Finally, the outer loop iterates over all edges to perform these checks, which confirms the total contribution of O, E² * alpha, V, from this critical and pseudo-critical edge processing step. Now, combining all the steps, we can determine the overall time complexity. Sorting the edges contributes O, E * log, E, while the critical and pseudo-critical edge checks add O, E² * alpha, V. When these are combined, the total time complexity becomes O, E² * alpha, V, plus E * log, E. Since the inverse Ackermann function, alpha, V, grows extremely slowly and is often treated as a constant, the effective complexity simplifies to approximately O, E² plus E * log, E. This highlights that the dominant term is the O, E² contribution from the double loop over edges. Moving to space complexity, we first account for the input edge list storage. Each edge has information about its endpoints, weight, and index, so storing these requires O, E, space. Additionally, the union find data structure uses 2 arrays, the parent array, which tracks the parent of each vertex, and the rank array, which helps optimize union operations. Both arrays require O, V, space, where V is the number of vertices. Also, we consider the space used by the recursive call stack in the find function. While the recursion depth could theoretically reach O log v, in the worst case, path compression significantly flattens the union-find tree, making this space negligible in practice. Another factor is the storage required for the output. Two lists are maintained to store the critical and pseudo-critical edges. In the worst case, all edges might be pseudo-critical, requiring O/E space for these lists. When we combine all these factors, the total space complexity of the solution is O/V plus E. This ensures that the solution is space efficient, as the complexity scales linearly with the input size, encompassing both the vertices and edges of the graph. Finally, let's compare this optimized approach with a naive one. A brute force method would involve trying all possible subsets of edges to determine which edges are critical and pseudo-critical. Constructing a spanning tree for each subset would result in a combinatorial time complexity of O2 to the power of E, which is computationally infeasible for larger graphs due to the exponential growth. In contrast, the optimized approach leverages Kruskal's algorithm combined with union find. By limiting the checks to only include or exclude each edge and efficiently constructing the MST and O/E asterisk alpha v for each call, the overall complexity reduces to O/E squared asterisk alpha v, a significant improvement. To justify the big O notation, the dominant term in the time complexity is O/E squared asterisk alpha v, arising from the nested loop over the edges and the union find operations. Sorting the edges, which is O/E asterisk log E, becomes asymptotically smaller as E grows, making it negligible compared to the O/E squared asterisk alpha v term. Furthermore, the space complexity of O/V plus E remains linear, ensuring efficiency even for large input sizes. This balance of time and space complexity demonstrates the scalability of the optimized solution. In this section, we'll highlight some common mistakes that can occur while solving this problem. First, failing to sort the edges by weight before applying Kruskal's algorithm is a critical error. Since Kruskal's algorithm relies on processing edges in ascending order of weight, skipping this step can result in constructing an incorrect minimum spanning tree, which will lead to misclassifications of critical and pseudo-critical edges. Another frequent mistake is misclassifying pseudo-critical edges as critical. Remember, pseudo-critical edges can still appear in other valid MSTs even when they are forcibly included. It's essential to verify the MST cost both when an edge is included and excluded to avoid this confusion. A third common issue is mixing up edge indices and weights. Since the problem requires you to identify edges by their original indices, sorting the edges can cause you to lose track of these indices unless you explicitly maintain a mapping. Finally, using an inefficient union find implementation without path compression or union by rank can significantly slow down the algorithm, especially when working with large graphs. Optimizing union find is crucial for handling the constraints efficiently. Now, let's consider additional pitfalls and practical insights. Ignoring edge cases in graphs is another area where mistakes can occur. For instance, disconnected graphs, self-loops, or multiple edges with the same weight need to be handled carefully during pre-processing to avoid incorrect results. Interviews often focus on your understanding of Kruskal's algorithm and union find, so it's vital to demonstrate how you modify the MST process to test edge inclusion or exclusion effectively. Clearly explaining this simulation step can leave a strong impression. Additionally, interviewers may ask you to discuss how your approach handles tricky cases like tied weights or disconnected components, so it's important to prepare for these scenarios. Don't forget to address time complexity as well. Sorting the edges takes O/E log E, and union find operations are nearly constant in time. Combining these steps gives an overall complexity of O/E log E plus E asterisk V, which is efficient for this problem. Let's now explore some related problems that can help deepen your understanding of MST concepts and union find. LeetCode 1584, min cost to connect all points, is a classic problem that focuses on constructing an MST using Kruskal's or Prim's algorithm. Similarly, LeetCode 1135, connecting cities with minimum cost, is another MST problem where cost minimization is the goal. On a slightly different note, LeetCode 261, graph valid tree, involves verifying whether a graph is a tree, which can often be done using union find to detect cycles. Lastly, LeetCode 947, most stones removed with same row or column, isn't explicitly about MSTs but relies heavily on union find logic to solve the problem. Tackling these problems will not only strengthen your grasp of MST techniques but also improve your ability to apply union find to various scenarios. Finally, let's consider some alternative approaches to solving this problem. While Kruskal's algorithm is typically preferred for edge classification, Prim's algorithm can also be adapted for this purpose. However, Prim's makes it more challenging to simulate the inclusion or exclusion of specific edges, which is why it's less commonly used here. Another option is brute force checking, where you manually test each edge's inclusion or exclusion by reconstructing MSTs for all combinations. While simple conceptually, this approach has a very high computational cost of O(e) squared asterisk log e, and is impractical for large graphs. A less common alternative is using dynamic programming to construct the MST. This method might work for small graphs, but it tends to be less efficient and less intuitive than greedy algorithms like Kruskal's or Prim's. Ultimately, understanding when and why to use these approaches is key to solving variations of the problem effectively. Great job! We've explored how to solve problem number 1489 using Kruskal's algorithm and MST concepts. Remember, mastering graph theory is essential for tackling advanced problems like this. If you enjoyed this video, don't forget to like and subscribe for more problem-solving strategies. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!